What is the science behind welding heat-affected zone changes? Imagine welding a metal piece and noticing that the area right next to the weld looks different from the rest. That's because of what is called the heat-affected zone. This zone is a part of the base metal that doesn't melt but changes because of the heat from welding. When you weld, you send a lot of heat into the metal, creating a temperature gradient that spreads outward from the weld. The area closest to the weld gets the hottest, causing microstructural changes in the metal. These changes can make the metal harder, softer, or more brittle, depending on the material and how fast it cools down. In steel, for example, rapid cooling can turn the heat-affected zone into martensite, which is very hard but also more brittle. That means it can crack more easily under stress. In stainless steels, especially high-strength types like duplex stainless steel, the heat can disturb the balance between the phases called austenite and ferrite. This imbalance can reduce the metal's resistance to corrosion and weaken its strength. The size of the heat-affected zone depends on how much heat you put into the weld, how fast you weld, and the material's ability to conduct heat. Metals with high thermal conductivity, like copper, spread heat quickly, making the heat-affected zone smaller. The main changes in the heat-affected zone include grain growth, which makes the grains in the metal larger. Larger grains tend to make the metal less tough. Phase transformations happen when the heat causes the metal's internal structure to change from one form to another. For example, in steel, heating and cooling can turn a softer phase into a harder one. Precipitates, which are tiny particles that strengthen the metal, can dissolve or form during welding, affecting the strength and hardness. Residual stresses also develop because of uneven heating and cooling. These stresses can cause distortion or even cracks if not managed properly. Controlling the heat input during welding is essential. Using lower heat input or faster welding speeds can reduce the size of the heat-affected zone. Post-weld heat treatments are often used to relieving residual stresses and temper hard microstructures. Choosing the right filler material and welding method also helps control the changes in the heat-affected zone. For example, using a filler that matches the base metal's properties can help maintain the desired mechanical qualities. Understanding how the heat-affected zone changes during welding helps engineers make better decisions. It ensures the welded joint is strong, durable, and resistant to corrosion. Proper control of the heat-affected zone is especially important when working with high-strength or specialized alloys. It's all about balancing heat input, cooling rates, and material properties to get the best possible weld.